modeling. So we're talking a lot today about modeling and drawing linear models for PCA. So I'll give you a bit of intuition as to how linear models work, how they're constructed, what kind of things to look out for when you're trying to fit a linear model. So the first thing I'm going to start is that we'll assume we only have two dimensions, right? So some y dimension, some x dimension. And we have some amount of points. So what does it mean to draw a linear, or to create a linear model? Is we want to create a model that uses x to describe y. So y will be our dependent variable because it depends on x, and x will be our independent variable. And how do we usually draw a line? We write out something like y equals a plus bx, where a is where the line would start, and b is some coefficient, as JC was mentioning today, coefficients in the model, coefficient that takes some portion of x or describes the slope of the line. So now, if I were to draw a line myself, I would go something like this, say. So I'd say that my intercept is somewhere slightly above 0, and b would describe the slope of the line. Now, why would I not draw a line something like this? Or like this? How would you decide what the right line should be?
Divide your variance.
Sorry?
Split up your variance.
Split up our variance.
Like split the error between both sides of the line.
Yeah, so we want to look at how far these points are. So basically our variance, or our error. So how far each one of these points is from our line. And we want to minimize that overall. We want all of the differences that we get to be as small as possible, or as low as possible. And we want them to be also normally distributed, because we don't want either only small errors and then one large error, or all big errors. So we want our differences to be normally distributed. So how do we judge how well the line fits the data? Or how do we decide if our variance is low enough? Yeah?
Iterate.
Iterate. Exactly. So we want to iterate because it's an optimization problem. So the thing that we want to iterate is we want to look at the difference. So say I have my actual or fitted y, and I want to take out the actual y. Right? So I have some value that represents the actual value, which would be like some y1, say, and I have my predicted value, which is going to be y1. I want to look at all of those differences. So I'll do I until n, and then I. And I want to take the mean of that, but first I want to square this. So why would I want to square this? Yeah.
You don't want the sign influencing. So.
Yeah. So we don't want the signs to actually somehow negate each other. We're actually interested in just the distance. So we want to square it, and then we want to take the mean of it all. And then at the end, we want to take a square root. So this is called the root mean squared. And it basically allows us to judge how well our line fits the data. So we know which one of these lines, so 1, 2, 3, how do we best fit it? And we try to optimize this value. Now, at the end of the day, after I fit my line, how do I decide if it's a good fit or not? I looked at the errors. So if my errors are normally distributed, that means all the errors say error 0, and then error 1, error negative 1. So I generally have something close to 0. There's a few errors that go to the positive, a few errors that go to the negative, but generally I have a normal distribution. Now what if my errors are distributed the following way? Would that be a good fit? No, because it means I have a lot of small errors or somewhere here, and then a few really large ones. So I'll show you later in the demo, but say I have my data and my data is like this. And I decided to fit a linear model, something like this, through it. My errors here will be large, 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 large. Some small, but generally large. So I'm going to have very imbalanced distribution of error in this case, pointing to the fact that my model is not very good. Okay, now giving an intuition just to generalize, how does this work in multidimensional cases? So what if I have not just x and y, but I have a, b, c, and I want to predict y, right? Or I'll end up with d. So I have multiple levels in this model. Why would linear modeling still work? Or how would you apply linear modeling? Yeah.
One variable at a time?
Yeah, you could look at it exactly one variable at a time. So exactly as GC was doing. So you have y and a, and you have some distribution, and you want to fit a model through it. You have another, so b and y, and another different distribution, and you want to fit a model. And each one of these models will contribute a coefficient. So in this case, we have coefficient b1, or in this case, oh no, b is bad. So beta 1, beta 2, and we'll basically get a different model that has, again, an intercept xo plus some beta 1a plus beta 2b plus beta 3c plus beta 4d. So basically we're scaling. We have a coefficient for every one of our independent variables, and we're scaling it by some factor to then predict our dependent variable. Does that make sense? Any questions? So I'll pull up the projector and show you it on a real example of a distribution. Sorry.
Does it have shake?
Very hard.
I see. So the idea would be just to show it on real data and how a linear model would be fit and the errors that will be generated because so I'll start by basically a normal distribution. So here I have normally distributed data, varying between -2 and 2, and I have, say, 100 time units. And this is just like I drew out like an x and a y axis and some data, and I'm drawing a linear model through it in red. So the thing that I would be interested in is how do my errors look? So in this case, since it's a normal distribution, my errors take a very normal distribution themselves. So the data generally fits very well to the linear model, and the errors are pretty normal. Another way that I can look at the errors is by doing a QQ plot. So I'm looking at the normality by looking how well it fits this line. And usually in a QQ plot, you look at the endings. So if the ends kind of fit well to the line, so basically fit the well the line of residuals or your errors, then you know that the fit is normal. And basically what this means is that the linear model is able to capture all the variance in the data very well. Now, if I have a quadratic distribution, so basically as I drew out, this is my data, and the red line is a linear model trying to approximate the data. And we can see very well that the linear model cannot very well approximate it because it doesn't have enough dimensionality. It can't describe the variance in the data. So in this case, if I take the errors this is the distribution of my errors that I would get. So I see that most of them are really large and at the beginning, and then I have a tail in the end. And similarly, if I try to use a QQ plot, I'll see how my tails here are not fitting in line with the errors. So, which means that the fit is not good. Two reasons why fit is not good is either your model cannot capture all of the information in the data, like in the quadratic model, because if the data is distributed as a quadratic model, the linear cannot model it at all, and it's missing a lot of the information. Another possibility is that you have bimodal distributions, so you have bimodal errors. So you have distribution in the data that changes over time, so it's non-stationary or not uniform. And then your errors show that there are two possible values, or two possible explanatory values. And that's how you know that the linear model is also not fitting the data well. Any questions?
So you take A, B, C, and D, you put it into a vector,
Mm-hmm.
and then you get a 4x4 matrix that would then describe your. Would a 4x4 matrix at that point help describe some correlations as a function of your dependent variable?
I'm not sure I understand what you're trying to do.
So if you have, y is equal to, so in this sense, y is equal to x, y is equal to some dot product, would be some dot product of like a B1, we have a matrix where B1, B2, B3, and B4 are diagonal, and A, B, C, D are a vector.
Oh, so you basically A and B are just a bunch of numbers. Then Y is also a bunch of numbers, right?
I mean, in terms of ABC, like that whole A, B, C, and D, that sum, everything in the sum there, that can be treated as a vector. And then you can treat that as.
So if they're treated as a vector, you have multiple.
So you have like A, B, C, D as a term.
A1, A2, until AX, something like that.
I'm thinking more, you actually have a vector, so it'll be something like, so beta will be a matrix, and beta will be some kind of tensor at that point, and you'd have A, B, C, like the vector itself, the four values that you're summing over 3 dimensions of the
I
vector.
think this is already the cross product of those vectors. Like your beta vector or beta variables would be in its own vector, and those would be the ones that you want to machine learn to figure out what their values would be to minimize this. So this is already the cross product, I think.
But you're talking specifically
So
about
basically
using
you have two matrices, right? And you're saying you have these guys here that you're trying to figure out, and you have a matrix of each one of your variables, and you want to just use the matrices to figure out then the Y matrix. Is that something you're talking about?
I'm thinking more about correlations, I'm thinking more just about figuring out correlations between these two variables and would they have an impact, how they would have an impact on the models.
Oh,
So
you mean
correlations
if
being-
you
yeah.
need to use a higher order model, so if you need some kind of B12 that looks at B1 and B1.
Yeah.
Oh, that's another thing you can do is when you try to fit a linear model, you look at the fit, and if the fit doesn't look right, what you can do is increase the dimensionality of your model. So by doing that, you're actually heading towards a quadratic model,
Okay.
right?
Okay.
And then, you can take your matrix or whatever, and you're just adding terms at this
Okay,
point.
yeah.
If you're adding A1, then
So it's basically stuff in terms of it.
another one, I don't know, 2, 3, and then
H.
C, CB, right? Of some sort. And you're basically adding until you get to B22, then B squared. You're basically guessing at that point of how many more terms do you need to include
Okay.
to describe properly the data. So in our case, if your data actually looks like this, right, you'll need a higher order term, which is x squared, and you don't need the lower order term, which is just x, right?
Okay.
Like in that model. And the way you can figure it out, JC was showing ANOVA, right? And usually when you do ANOVA, you can tell it to, it's basically analysis of variance. You can see how much of the variance is described by what component. And if you notice that relationships between components describe a lot of variance, you may decide to then model the relationships and not model the components themselves.
Okay.
Yeah.
I'm not aware of using a correlation matrix specifically in the machine learning portion of a linear model. If that's what you're thinking of.
Okay.
Do you think there was a
No,
method that
just
uses that, or?
no. I guess something just got crossed. I'm just gonna just two ideas just got crosswired in my brain or
Okay.
something.
Maybe somebody does that. I'm not sure. But in traditional linear modeling,
Okay.
you just solve for
Okay.
and the arrangement is a lot like you're thinking.
Yeah.
Especially if you're doing modeling of factor combinations, like
Yeah.
interaction.
Alright, well, thank you for coming out, and do let us know if you have any comments again, and yeah, thanks.